So what this brings to us to now is where we're going to be for the next, well, probably at least month or so in this course. And what that is getting into how do we identify compounds? So you're in the lab, you run a reaction. And it's very, very likely that you get something that looks like this. A bunch of white solid. Or maybe you get a colorless liquid. How do you know if it's the product that you wanted? So early on in this course, in the lab portion, we learn about melting points. So we can take a melting point of this. It's a solid. See what temperature it melts at. But there's two problems. The first is that that's only useful if this is a compound that someone's made before, and you know what the melting point is supposed to be. Now, for what you do in lab, that's usually not going to be a problem. But for someone doing research, it's not uncommon to make a molecule that no one's ever made before. And so in that case, yes, you can take the melting point, but it doesn't really tell you anything. The second half of that as a problem is that at one point I did a search for compounds with melting points of 110 degrees Celsius. I got back over 400 different compounds. And so what this tells us is that while melting point can be useful, and there's a lot of information we can get from that, but overall, it doesn't give us that much information. And so a melting point is just one technique that we have to use with many other techniques to figure out what the identity of a molecule is. So what becomes more useful and more important are techniques of spectroscopy or spectrometry. Now, some of you may have a small amount of experience with spectroscopy. You may have done a little bit of IR, infrared spectroscopy analysis at the end of General Chemistry 2, where you were trying to identify the difference between, I believe, a carboxylic acid and an alcohol, and maybe one other functional group. But we're going to get into these techniques in much, much greater detail here. So when we talk about spectroscopy, from the simplest point of view, we're looking at the study of the interaction of energy with matter. And depending on the type of energy used, you get many different types of spectra, which can give you many different types of information. And so ultimately what spectroscopy turns into, and this is why it's one of my favorite areas of organic chemistry, is it ends up giving you a puzzle to solve. So you collect, in our cases in the lab, we'll get one or two or maybe three different types of spectra for a compound and try and figure out what it is. In more complicated situations, you might have 10 or 12 different spectra that you're looking at of the same molecule, trying to figure out different structural features of the compound. Now, why do we have so many different types of spectroscopy? So in this class, we're going to learn about infrared spectroscopy, proton NMR, carbon-13 NMR. We'll learn about mass spectrometry, and we'll do a little bit with ultraviolet spectroscopy. Well, the problem is that no one type of spectroscopy gives us all of the information about a molecule. So in general, most of these techniques apply the following principles. So we take our sample and we expose our sample to some sort of electromagnetic radiation. For example, infrared. Then we analyze the molecule's response. The computer gives us a spectrum, and then we have to interpret those results. And so some of you may be wondering, especially if this course is being taken under circumstances where we're only doing the lecture and we were not able to offer the lab. This is the main reason that the organic chemistry lab is so difficult to offer in an online setting. Why is that? Well, we do a lot with spectroscopy in the lab. That's how we identify all of our products. And this is something that can't be duplicated at home. The instruments that we use for spectroscopy, even our cheapest instruments, which are the infrared spectrometers, they cost almost $20,000 a piece. So there's no way to duplicate that at home. But what happens is in many of these techniques, we start with our electrons here in the ground state. And if you hit these samples with the exact amount of energy, this delta E, those electrons can move up to the excited state. Now, it's important to remember that these processes are what we call discrete. What that means is this will only occur if you apply exactly delta E to this system. If you apply any other energy, then this excitation won't occur. And the second thing is not all excitations are allowed. But it's very often the process of these electrons moving to the excited state and then returning to their ground state, which gives off energy, that is what gives us some of our spectral, or a lot of our spectral information. So you may recall from general chemistry that the change in energy is equal to Planck's constant times the speed of light over the wavelength. And so we can then talk about what are some of the different types of spectroscopy that we can do, and what information do they give us. So here's our region. Here's our wavelength in centimeters. Here's our energy. What units do we use for energy? So here's one of those annoying things that organic chemists do. You just spent the whole year in general chemistry and you did everything in kilojoules. And organic chemists are stubborn for some reason. We use kcals. We'll talk about what energy is being looked at, and then what information do we get from this type of spectrum. And this is the other thing that makes spectroscopy can make it very expensive, because every one of these different regions that you'd want to operate in requires a different instrument. So we'll start with X-ray. X-ray operates at very, very low wavelengths, 10 to the minus 8 to 10 to the minus 7 centimeters. Now, if you recall the equation on the previous page, delta E is equal to hc over lambda. If the wavelength is low, what does that mean about the energy? Well, that means the energy is very high. X-ray looks at inner shell electrons. And the information we get is the complete structure of the molecule. Well, if X-ray gives us a complete structure of the molecule, why do we need any of these other techniques? So I think the best way to talk about that is to tell a story. So back when I was in grad school and I was finishing up my PhD, the very last thing I needed to do was to get an X-ray structure of a molecule that I had made. Now, there's two things about it. Number one, the compound has to be a solid. But not only does it have to be a solid, but it has to be a solid that will form a crystal, and a crystal in a single way. And so it turns out it's not a trivial process to get one of these crystals to form properly. In fact, it took me about a month to get decent crystals of this compound that I could take to our crystallographer and get a confirmation on the structure. Meanwhile, something like an IR spectrum takes about 90 seconds. Once you're used to using that instrument, an NMR might take 5 or 10 minutes. And the worst part of the story was the way I did this was using different combinations of solvents in order to make the crystals. And the combination of solvents that I used was just a pretty bizarre choice. And when I went and told my advisor that I had finally gotten the crystals to grow and had my structure, he said, "So what solvent did you use?" And I showed him, and he said, "Why'd you pick that?" And I, gave some sort of reason that made sense. But the reality was I'd been trying to do this for a month, and I walked over to our shelf of solvents the day before and just kind of picked one that I hadn't used before. And, well, got lucky. It worked. But that's why we don't just get rid of all these other techniques. X-ray, when it works, is extremely powerful. The problem is it doesn't always work that well. We can also use ultraviolet. This is slightly longer wavelength, which means a little bit lower energy. Here we look at the valence electrons. And we're looking at what we call chromophores. And in a lot of cases, this helps us to detect conjugation within molecules. We can also put visible light on here. The visible light isn't really that important, but we'll put it on here for completeness. Again, a little bit longer wavelength, a little bit lower energy. Still looking at the valence electrons. And really, this is whatever is visible, the colors of the compound. IR, or infrared, one of our two most important techniques. Again, a little bit longer wavelength, higher energy. Here we're looking at vibrational energies, which we're looking within the bonds. And this shows us functional groups. So in other words, on an IR spectrum, you get one peak that would represent an alcohol versus another peak that might represent a ketone. I'm going to skip over microwave because that's not something we really will use ever in this way, and go to our most important one, which is radio, or NMR. NMR, very long wavelength. We're talking about wavelengths of 100 to, upwards of 100,000 centimeters. That means these waves are very, very low energy. And we're looking at what are called nuclear spin states. We'll explain what that means later on when we get to the NMR portion. But this gives us two things. It gives us the structural environment an atom is in, and it gives us connectivity. So as we'll learn when we get to NMR, NMR is the single most powerful spectroscopic technique that we have. It gives us the most information of any of our types of spectroscopy. So this is our introduction to spectroscopy, and after this we will jump right into infrared.